Hello everyone, my name is Andrew Manzi, Technical Marketing Manager at Autodesk, and welcome to this brief course on mobility simulation, Know the Basics. Module number 5, COVID-19 Considerations and Application. Okay, so in this module, what I really want to get across is to make you aware of the available features and various settings and parameters that are useful in mobility simulation, um, directly specific to COVID-19 planning. We'll also go through some of the general considerations around this, and then how we can uh, implement those considerations using the various parameters and settings within the software. Okay, so what's changed? Well, it boils down to four main areas: flow, capacity, ingress, and circulation. So the first one really, occupancy or space. Um, the old occupant loadings of 6 meters per square meter per person um, no longer apply because we need more space to maintain safe distancing. Um, in retail, stores can now accommodate fewer people. Schools may have to have smaller class sizes, and also the productivity per unit area is now reduced. So space has now become more valuable than ever. With regard to routing, extra space is required, and that severely limits door and passage capacity, obviously. And the understanding that we previously had around the measurement of one-way flow needs to be developed quite a bit further. We're also looking to reduce crossing flows with our routing, and maybe we need to also consider erecting partitions. So also risk has changed. So previously life safety was based around fire protection and evacuation from any one particular area or building. Now infection has been folded into that. So we're now looking at infection, transmission, as well as fire protection and evacuation. Although as the virus subsides, this might rebalance over time. Speed and flow obviously will change. Now, people will generally be walking at the same speed, but the enforced spacing will result in lower flow rates in general, and it's going to take a lot longer to load and unload people from transport systems. Okay, so in terms of developing the networks, we're going to be looking at these five areas. So we need to consider physical distancing, unidirectional flows, dedicated parking, assigned entrances and exits, and also consider staggered arrival times and departure times. So as far as network design is concerned, when we're looking at unidirectional person flow, parking, and the entrance and exit issues, we'll be looking to incorporate those into the network layout itself. And then for physical distancing, we'll be looking at the people and walkway parameters. So we have a video here that covers most of those particular issues. We've never been more conscious of how we move through the built environment. From door-to-door journeys to physical distancing for queues, understanding system efficiency is essential for optimizing for safe and free movement. Under normal conditions, people arrive at the office within a short time window, parking randomly, and travel to the nearest entrance. This can give rise to close contact at congested entrances and exits, both in and outside of the building. There are many mitigation measures that can be used to assist with managing personnel routing. Outside of the building, staggered arrival times, a longer arrival window, and assigned parking positions, combined with dedicated entrances and exits, can all help to relieve pressure in these critical areas. Inside the building, measures such as restricting elevator usage to accessibility purposes and for travel to uppermost floors can reduce the opportunity for close contact. Maintaining physical distancing and implementing unidirectional travel patterns will also help to minimize proximity issues. Mobility simulation can assist in gathering people movement data, such as individual journeys, elevator usage, and crowd behavior, which is vital to the understanding and design of managed personal routing systems. This important data can be used to inform policymaking by bringing data-driven insight to physical distancing and efficiency of travel to ensure a safer working environment. So let's have a look at the parameters that we can use to affect the physical distancing, for instance. So if we look at person parameters, we'll see under the size tab that there is a field for spacing. And so if you look in the top section, we'll see that with a spacing of 0.3 meters, people are bunched up as you would expect them to be. However, if we look at the example below where we've increased the spacing to 5 meters, then the agents are spaced out appropriately, and they will try to maintain that as they're traveling around the route. So as well as properties around the people, we also have walkway properties which can help us maintain physical distancing. So in the top example, what we have done is we have divided up a walkway into shorter lengths and then activated the private property so that only one person at a time can enter each one of those short sections. Now, alternatively, what we can do is we can leave the walkway in one piece, if you like, but then set a capacity. So there's a capacity field where we can enter the value, and no more than that number will enter that particular walkway at one time. And then we can also use that in combination with the spacing person parameter, which we saw on the previous slide, to maintain a safe distance. Okay, so we've now got a number of different examples of where these properties and parameters have been applied and what effect we can see from them. So for this airport example, we're going to look at 3 different conditions. We're going to look at the normal pre-COVID conditions with no limitation on movement. And then we're going to look at the effect of just applying the physical distancing constraints, see what effect that has, and then we're going to look at a third condition where we have the physical distancing constraints activated plus some infrastructure changes, and we'll see what that looks like. So some of you may have seen this example earlier in the course. In this case, we're going to use it to demonstrate how we can simulate and identify the different effects of different measures taken to mitigate COVID-19. We're going to look at the departures area in this airport and look at three different conditions at various timings. Firstly, normal pre-COVID conditions, then physical distancing implemented only, and then lastly, physical distancing and infrastructure changes implemented. So at the beginning, we only have this single lady making her way through. But as we move on to 15 minutes, we can see there's a few more people um, in there, but there's no real queuing to speak of. And then if we push forward to a 27-minute slot, we can see that the queues are starting to build up. People are quite close together, as you would expect. It's what we're used to in airports. So let's just take away the infrastructure then, just concentrate on the actual simulation. So moving to a simulation where everything is exactly the same, but just implementing the 2 meter physical distancing. We'll see again just that lone person. Moving forward to 15 minutes, you can see people are spaced out a little bit more. The queue is a little bit longer, but it seems quite manageable. But then if we move forward to 27 minutes, we can see that we've now got a big problem on our hands. The queue is backed up all the way into security, and that's going to cause its own problems. So we need to solve that. So really what we need to do is to increase the capacity of this area. So even though the loading is the same, we need extra capacity. So by increasing the area of the queuing and also more of the tellers, we can, even at 27 minutes, we can see everything is still flowing quite freely, and that is actually working. Okay, so this next example is a supermarket example, so typical retail, and we are going to consider the same three conditions, um, the pre-COVID ones, physical distancing, and then physical distancing plus infrastructure changes, including a unidirectional flow design. Okay, so we're going to have a look at this retail example. So we have a layout here of a fairly typical supermarket, and what I want to do, I want to concentrate on the movement of people in this center section. So people will arrive through these doors here, they'll mill around in this main display area up into the frozen section, backwards and forwards until they have everything they need. Then they'll file down through the checkouts and eventually they'll come out. So let's move into mobility simulation and see what we can do there. Okay, so we're in mobility simulation now. So we can see we have the floor plan, and I've put some zones in here just to simulate the display cases and the cashiers. So let's just have a quick look at what we've done with regards to the people themselves. So we've basically set up two different types of people. We've colored them differently, and if we go to motion, we'll see that I've changed the speed just to simulate different people moving around at different speeds, generally speaking. And we also have the lanes set up so that people will walk through lanes in between the cases slower than when they're walking around the outside to simulate people looking at items on the shelves. Okay, so let's run the simulation and see what happens. So we can see people entering in this from this entrance here, and they're generally just walking around. Um, no rhyme or reason to it, just randomly walking around, pretty much as you would expect to see before we've applied any of the COVID mitigation measures, and this is how it used to be. And so eventually, once these customers have done their shopping, they move down to the cashier, and then they leave the supermarket. Okay, so let's see what might happen if we were just to employ physical distancing and no other measures. So if we go up to parameters and people, um, if we go to the size tab, you'll see that I've increased the amount of space required around each particular person. So as much as possible, um, this will be maintained. There may be certain circumstances where it isn't possible, and we'll see in a moment what that is. Okay, so we'll say okay to that, and then we'll run the simulation and see what happens. So here we can see people entering the supermarket. Um, generally speaking, are trying to stay away a safe distance. But what we will find is that without any infrastructure changes, we'll get bottlenecks, um, and this is where basically the network is failing, and we really need to do something about that. So you can see here where we have areas where there's not enough space for all those people to file through, and they have to negotiate their way around that. And we'll get more and more of that as more and more people file in. But eventually they will come out and go through the cashier and leave. Okay, so in addition to the physical distancing measures, um, in this particular simulation, we've made some changes to the infrastructure and how people are to be moved around. So in this particular case, we have the physical distancing is at the same level, so 2 meters, same volume of people over the same amount of time. But what we've introduced is a low level barrier here to separate people into these two lanes. And then we have a unidirectional flow for the customers to follow. And then we also have this circular area where we can move around a little bit more easier and through the center here. Okay, so let's see what that does. We'll run the simulation. So you can see how people are entering, choosing the area that they want to go to, but adhering to this unidirectional flow pattern. Areas where people are coming together are much reduced. And after a period of time, they do actually go to the cashiers and eventually leave.